All right. Good afternoon, everybody. I hope you guys are all healthy and staying safe. Today we are going to be talking about gel electrophoresis, and this is just going to be a quick overview of gel electrophoresis. So, first, what you need to know or remember is that DNA is negatively charged because of the phosphate backbone. Remember, DNA is made up of nucleotides, sugar, phosphate, sugar, phosphate, and at every sugar is a nitrogenous base. So we've got our phosphates and our sugars, and then a base, and that makes up a nucleotide. Here is another nucleotide, and we have our phosphates. So the phosphates are what carry, the important part is what carries the negative charge. Now that negative charge is very important because when we run electricity through a gel and there is DNA inside that gel, DNA will be attracted to the positively charged side and it'll be repelled from the negatively charged ones. Just like we know opposites attract, likes repel, so we know that very well. And when you run a gel, the very first thing you have to do is make a gel. So first you pour the liquid agarose into the casting tray, and then you put this comb in it. Now basically the comb is just there to leave a space for you to put your DNA in. So after the gel or agarose solidifies, the comb is removed, and that leaves wells or spaces for DNA. The DNA samples are mixed with tracking dye, which contains sucrose, which helps you to visualize the DNA migration. Also, in a gel, you have the gel covered by a buffer solution. It's just a solution or liquid that helps to conduct electric current because, of course, electric current is what is moving the fragments of DNA. So, let's look at that. So we have our gel tray. We pour our gel into the tray and then we add our comb, and that comb leaves wells or spaces once it solidifies. We take the comb back out and now we have spaces to place the DNA fragments, or just DNA, I should say. Let's just put the DNA. So the DNA goes into the wells, and this is all happening in the gel electrophoresis box. Here we have the negative end, here we have the positive end, here we have our gel, and here's our well where our DNA started. Now we turned the electricity on. Here's our buffer in blue. We turned the electricity on, and the electricity ran from a negative to a positive through our gel, and it moved away, the DNA moved away from the negative end towards the positive end. And based upon the fragment size will be how far that DNA segment migrates. So here we have the largest molecule in base pairs. So let's say this would be 150 base pairs. And we have the smallest molecule down here at 20 base pairs. Now, if you don't remember what a base pair is, just remember that A, T, C, and G always bond together. Each one of these is one base pair. So if you have a segment of DNA that is A, T, C bonded with G, A, T, this segment of DNA would be 3 base pairs. All right, we're going to talk more about base pairing and what actually cuts DNA here in just a little bit. So another basic picture of gel electrophoresis. Here is our buffer, which is our solution that helps to conduct electricity. Here are our wells that start the DNA or hold the DNA until we turn on the electric current. We turn on the electric current, it runs through the gel from negative to positive. DNA has a negative charge, so it moves away from the negative towards the positive, and then we get our movement based upon the size of the fragments. The larger sizes have more friction. The smaller base pairs or the smaller size fragments have less friction, therefore they move faster through the gel. So this is just a picture of the full setup. There's a power supply, of course. We have the negative and the positive end. We have all of this tan stuff, which is buffer. We have our gel, which is right here. And we have the wells, which we started out in. Wells for the DNA. So the DNA started in these wells. Then we turned on the electricity. The larger fragments moved slower, the smaller fragments moved faster. And if you ran this gel too long, literally all the DNA would pile up at the end, opposite end of the gel. So you have to make sure you don't run your gel too long or you lose your fragments. Now, how do the movements of DNA fragments in agarose gel works? Basically, it's a logarithm based upon its size in base pairs, like I talked about before, but it's simple. The larger molecules move more slowly because of friction. Slower molecules move more quickly. Now, in order to see DNA, we have to visualize that DNA, or we have to stain it first, I should say. And we stain it with something called ethidium bromide. Ethidium bromide, under normal light you can't see, but under ultraviolet light gives a nice purple glow. It's excited by ultraviolet radiation. So the gel, prior to running the gel, is soaked in, or actually could be post running the gel, is soaked in ethidium bromide solution, and the DNA bands soak up the gel, so that we soak up the ethidium bromide, so that we can see that. We're going to take a look at a picture of that in just a second. Then the gel is placed under UV light and visualized and or photographed. And it looks like something like this. So now we have a picture of the segments or bands of DNA that are in each one of these wells. So once again, here's our negative end, here's our positive end, make it better positive, there we go, and electric current running from negative to positive. Our DNA is being held in these wells, so this is where our DNA was. We then turned on the electric current, and these segments began to separate based upon the number of base pairs. So let's say this one is 200 base pairs, and this segment way down here, a fragment way down here, is 15 base pairs. Now, of course, anything in the middle from that, talking about that one right there, anything in between that's going to be a different amount or size of base pairs depending on the size of the fragment. And this can be used to figure out crime scene data. So let's say that this well right here, get that off of there. There we go. This well right here is our crime scene. Uh-oh. Technical difficulties. Hang on one second. Okay, I think I'm back in business. Nope. That's not an option either. What I'm going to do is I am going to hit pause, or actually go back, and I'm going to finish this in another video. So this video is done for now, and we can go back and look at this. I'll start off from that picture again, talking where I left off from there. Hopefully I can get this figured out.